Now suppose we've got a plane, and a point P naught is x naught, y naught, z naught is living on this plane. So what other information describes the entirety of this plane? Well, let's think about that for a second. We've got a plane, a poorly drawn one at that, and you've got some point, P naught is x naught, y naught, z naught, that's sitting on this plane. So my question is, what other information can help us figure out what the entirety of the rest of the plane looks like? Anyone get a idea about what we might want to do for this? It's a similar idea to what we had last time. It's a similar idea to what we had with the direction vector, but a plane doesn't have a direction per se. Here's what we can do. What we're going to do is we're not going to find a direction per se, but what we're going to do is we're going to find a vector that is orthogonal to the entire plane. So if you've got some other points on the plane, then the displacement vector is on the inside of the plane. So let's look at that for a second. You've got a point P naught, x naught, y naught, z naught is on the plane. And then P, x, y, z is also on the plane. So you've got this vector, which is here, that's going from P naught to P. Well, there's going to be some vector, which we're calling n for normal vector, that is orthogonal to that plane. So let's think about that for a second. You've got some vector that's orthogonal to the entire plane, and you've got another vector that's between them. So what's their relationship? What can we say is the relationship between, so r minus r naught, which is the displacement vector. So what's the relationship between r naught, and n? Can anyone see what that would be? What's the relationship between r naught, and n in this case? What we see is that r minus r naught is orthogonal, and n's not quite the cross product. It's not, because for cross products you need a second vector. And we only have one vector that's inside the plane. The vector inside the plane is r minus r naught, but they are orthogonal. And it's a little bit simpler than a cross product. They're orthogonal, but we're not going to use a cross product. We're actually going to use a dot product. That tells us, in other words, that r minus r naught dotted with n, if they're orthogonal, then that has to be equal to zero. That's right. So that means that r minus r naught dotted with n is equal to 0. Okay, now that's very helpful for us. So let's see. So they're orthogonal. Now, if you unpack all that, r minus r naught, that's just x minus x naught, y minus y naught, z minus z naught. So if you unpack all that, you get what's called the scalar equation. A times x minus x naught plus b, y minus y naught, plus c, z minus z naught, that's all equal to 0. What does that tell us? Well, a point x, y, z is on the plane with the point x naught, y naught, z naught, and normal vector ABC, only if the numbers x, y, and z all satisfy this boxed equation, which is very important for us. So let's suppose you want to find the equation of a plane that's going through the points 2, 4, negative 1, and with normal vector 2, 3, 4. So let's try this. So let's try figuring out what this looks like. So 2, 4, negative 1, and 2, 3, 4. So with that point, just recalling that we've got a times x minus x naught plus b, y minus y naught, plus c, z minus z naught. That's all equal to 0. 2, 4, negative 1. There's our x naught, y naught, z naught. And our 2, 3, 4, that's our n is equal to ABC. So with all this in mind, this gives us 2 times x minus 2 plus 3 y minus 4 plus 4 z plus 1 is equal to 0. There's your equation for the plane. That's it. Or if you prefer, 2x plus 3y plus 4z, just distributing these numbers inside of it, all comes out to be 12. Both of these work. Both of these are perfectly valid equations. The second one is a little more concise. The first one has the advantage of immediately having a point that's on the plane that we can see. 2, 4, negative 1 is inside of the terms of x, y, and z. And we can always write it in either of these forms, either as the scalar equation that we had before, a x minus x naught plus b y minus y naught plus c z minus z naught is 0, or you can do it as ax plus by plus cz is equal to d. Now, if you do it the second way, you might not immediately be able to tell what a point is from this equation, although sometimes it's not very difficult to do that. But we do have a normal vector. Still, ABC is the normal vector. A, B, and C, these coefficients, A, B, and C, from before, are the same A, B, and C that you'd multiply in for all of those coefficients. Okay, so here's a follow-up question. What are the x, y, and z intercepts of this plane? Let's try to think about that for a little bit. Well, what are the x, y, and z intercepts? So just to recall, our plane that we had is given by 2x plus 3y plus 4z is equal to 12. Let's think about what this looks like. This is very much not to scale, but please bear with me. You've got your x, y, and z axes, and you've got a plane that is intersecting these three axes. So the question is, okay, what are the intercepts? Well, the x-intercept is going to happen when y is 0 and also z is 0. Right? It's this point over here when x, y, and z are well, I don't know what x is, but y and z are definitely going to be 0. So if those are 0, that tells us that x has to equal, can we see it? Well, 2x is going to be equal to 12, which means x is 6. So the x-intercept is 6, 0, 0. We can figure out what the y-intercept is similarly. 3y is 12. So the y-intercept is going to be 0, 4, 0. What about the z-intercept? Well, in that case, we have 4z is equal to 12, which says that the z-intercept is going to be 0, 0, 3. So there are our intercepts for this plane. You've got 6, 6, 4, 3, all for this same plane. All right. So questions so far? Okay, so what if you have the equation of a plane that passes through 3 points? You could, for example, look at a plane and try to figure out what the plane looks like coming from 3 points. Well, once again, you have that the scalar equation is the same thing that we had before, right? It's the ax minus x naught, b y minus y naught, c z minus z naught. That's all going to be 0. and x naught, y naught, z naught is the points on the plane, and ABC is a normal vector for the plane. So you need a point on the plane and a normal vector that's orthogonal to the plane. Well, the good news is we have the point. Any of P, Q, or R will do the trick. So let's say, for example, we take P. So x naught, y naught, z naught is going to be 1, 3, 2. Still, we're going to need to find what the normal vector is. So how are we going to do that? Well, what do we need? We need a vector that's orthogonal to every vector contained in the plane. So if here's our plane, this is obviously not to scale, but it doesn't really need to be. We can imagine shifting our perspective as need be. Here we've got P, and here we've got Q, and here we've got R. And actually, I want to flip Q and R. So here's R, and here's Q. And we want a vector that's orthogonal to every vector in this plane. In particular, it's orthogonal to the vector PQ, and it's orthogonal to the vector PR. This is the vector we want, n. And it's orthogonal to both of these things. How are we going to find that vector n? We want a vector that's orthogonal to both of these. How are we going to find it? Now we can hit it with a cross product, right? Because if n is orthogonal to PQ and PR, the best way to do that is to get the cross product. So n, we can just write that as the cross product of PQ cross PR. This, by the way, is why I wanted to flip those so that it obeys the right-hand rule. So we calculate our cross product, IJK. For, in this case, PQ is 2, -4, 4. PR is 4, -1, -2. In this case, this is going to be 8 plus 4, I, J, so subtract -4 minus 16, J, K, so plus -2, plus 16, K. Or in other words, this is 12I plus 20J plus 14K. We can check this by taking the dot product with the original two. So that's going to be 2 times 12 minus 4 times 20 plus 4 times 14 is 24 minus 80 plus 56 is 4 times 14. That is indeed 0. And meanwhile, we have 2 times, oh, sorry, not 2. Meanwhile, we have 4 times 12 minus 20 minus 2 times 14, and that's going to be 48 minus 20 minus 28, which is again indeed equal to 0. So good. We know in that case that we've calculated our cross product correctly. And with that in mind, we can now go about doing this. We know in this case that that we've got the point. The point that we have was the point that we're going to use is P is 1, 3, 2. So we can write that as 12 x minus 1 plus 20 y minus 3 plus 14 z minus 2 is all going to be 0. That is our plane equation. That will give us the equation for this plane with these 3 points. Okay, so that's great. That's a very big step in the right direction for us. However, Now let's think about that. So that's the exact answer we had. We can also write that as 6x plus 10y minus 7z equals 50 after doing some algebra. Now I want to point something out here. The normal vector that we had to begin with here was n is 12, 20, 14. Here, the normal vector was 6, 10, 7. Notice that this is 2 times the vector 6, 10, 7. Are they both normal vectors? I mean, can they both be normal vectors? Sure, they're parallel. If one of the vectors is parallel, excuse me, if one of the vectors is orthogonal to the entire plane and the other vector is just parallel to it, you can think about that for a second and you'll realize that, that both of them are going to be perpendicular to the entire plane. We don't care about the length of the normal vector. The length of the normal vector, and for that matter, the length of the direction vector for lines, that's not important. We don't care about how long it is. We only care about the direction of these vectors. Even considering the direction, there are really 2 different directions that we're okay with, just opposite directions. So we found 12, 20, 14 was one of our normal vectors. I don't really care about that. In fact, that's kind of a clunky looking vector. We can make our lives a little bit easier by factoring out a factor of 2 and taking the normal vector to be 6, 10, 7. But it's important to keep in mind that these vectors are not the same. They're not equal vectors. They're parallel, and the fact that they're parallel means that they encode the same information for us. Because in this specific context of finding, this specific context of finding these the plane equations, we only care about the direction. Okay, so with all that in mind, let's move right along. So what if we want to, so here's a different problem. What if you want to find the point at which this line with these parametric equations intersects this plane equation? I want to go back to what I said before. What I said before was that a point xyz is on the line only if there's some t satisfies the equations. And also this point xyz is on the plane only if the numbers, only if these x, y, and z satisfies, only if x, y, and z satisfies the plane equation. So in other words, to find where they intersect, x, y, z, if x, y, and z is a point of intersection, then all equations, all of them together, must be satisfied. So let's think about that for a second. We've got x is 2 plus 3t, y is negative 4t, z is 5 plus t, and 4x plus 5y minus 2z is equal to 18. All we're going to do is substitute x, y, and z in for the plane equation. So that's going to give us 4. We're just doing algebra at this point. So this 4 times 2 plus 3t plus 5 times negative 4t plus, minus 2 times z is 5 plus t. Unraveling all of this, this is 12 minus 20, 12, let me try that again, is to say that 8 plus 12t minus 20t minus 10 minus 2t minus 10 minus 2t is all equal to 18, or in other words, 12 minus 20 minus 2 is to say that negative 10t is equal to 20, right? That's going to be 8 minus, actually that's not quite right. No, it is right. So 8 minus 10 is negative 2. Add 2 to both sides, you get 20. So in other words, t equals negative 2. Now we're not done. We haven't found the point of intersection. What we need are the point is the point where they intersect. So we found what t is, but again, that's going to satisfy the x, y, and z parametric equations. So we're basically done at this point. We have x is equal to 2 plus 3 times negative 2. Y is equal to negative 4 times negative 2. And z is equal to, z is equal to 5 plus negative 2. So I'm kind of going backwards here in my directions, but the point that we're interested in finally, at the end of the day, 2 minus 6 is going to be negative 4, comma 8 for the y, and 3 for the z term. This is the point where they intersect. Okay, very good. So negative 4, 8, 3. That's the final answer to this particular question. Questions from anybody else? Come on, what just happened? Okay. So questions? Okay, so if there are no questions. Now, meanwhile, two planes are parallel if the planes never intersect. So, which is reasonable to think about, right? You've got two planes. Now, we can't really talk about, we got to be careful when we talk about lines and whether or not they intersect in 3 dimensions, because in 2 dimensions, it's easy. They either intersect or they're parallel. That's not true in 3 dimensions, but it is true for planes. So planes are either parallel or they intersect. And if they're parallel, well, this is the figure that we have. But how do we tell if 2 planes are parallel? Well, here's one normal vector. And here's the other normal vector. And what do we notice about the relationship between the 2 normal vectors? If they're parallel, that means the normal vectors are also parallel. So the normal vector of n1 is going to be parallel to n2. We stare at that for a minute and we realize that makes a certain amount of sense. So meanwhile, the angle between 2 planes, well, you can just think about that as the angle between the normal vectors. Because if the normal vector for the first plane is perpendicular to that plane, it's basically basic, high school, middle school geometry, and you can see that these angles, this theta between the normal vectors and the theta between the planes, really ought to be the same, and it is the same. Okay, so what about the angle between the planes x plus y plus z is 1 and x minus 2y plus 3z is 1? Well, the angle between them is the angle between the normal vectors. And we know what that is. That's going to be 1, 1, 1, and 1, negative 2, 3. So how do we find that angle? Let me ask the question a different way. How, in general, do you find the angle between two vectors? We've got a formula for that. We're going to use the formula that says that n1 dotted with n2 is the magnitude of n1 and n2 times cosine of the angle between them. Okay, so with that in mind, we can say that n1 dot n2, here's what it is. So in other words, let's apply that to our problem at hand. So we've got n1 is 1, 1, 1. N2 is 1, negative 2, 3. So their dot product, we know n1 dot n2 is 1 minus 2 plus 3. 1 times 1, 1 times negative 2, 1 times 3, add them together. That's 4. It's not 4, it's 2. Excuse me. So meanwhile, n1 has got a magnitude of root 3, n2, 1 plus 4 plus 9, it's got a magnitude of root 14. The upshot of this is that we've got 2 is equal to root 3 times root 14 cosine theta. So cosine theta is just arithmetic at this point. Root 2 over root 3 times root 14, or in other words, 2 over root 42. And if you really want to, you can write this as 2 root 42 over 42, or in other words, root 42 over 21. I mean, it's fine either way. It makes no difference. You can either leave it as 2 over root 42 or root 42 over 21. It makes no difference to us. Either way, theta is simply our cosine of 2 over root 42. And that's about the best you can do. We're not going to ask you to do any ridiculous calculations. You can just leave it in that formula. If you really needed to, you can figure out what the decimal expansion is, but we're not going to worry about that too much. You're not going to need to do any calculation beyond this point on one of our exams, for example. Okay. So what if you want to find the symmetric equations for the line of intersection between these planes? Because if you've got 2 planes and they intersect, they're going to form some line between them. And what do you need? Well, you need a point on the line, and you need a direction vector that's going to be parallel to that line. And in that case, what's that going to look like? Direction vector parallel to that line. Well, the point is, let's start with a point. So you've got the planes x plus y plus z equals 1, and x minus 2y plus 3z equals 1. We need a point on both planes. Right? Because if we're going to have a point of intersection, it's going to have to live on both of these planes simultaneously. And what point should we use? What's a point on both planes? Stare at this for a second, we can see what the answer to that is. Well, an answer anyways. A point on both planes, here's 1, 1, 0, 0. That's on both planes. Plug in 1, 0, 0 in for x, y, and z. It's going to satisfy both equations. So yeah, that's a point on both planes. What about the direction vector? That is a little bit trickier. But let's think about that for a second. The direction vector. The direction vector is going to be in a vector that's inside of both planes. So let me say that again a little bit more clearly. So the direction vector it's going to be inside both of these planes, right? So if you have your first plane, it's going to be a terrible drawing, but bear with me. So here's one plane. Here's another plane, and they're intersecting. right? And we know that the direction vector of that intersection is going to be inside of both planes. We see that, right? That the direction vector for this line is going to be inside of both planes. What does that really tell us, though? That means that V is going to be orthogonal to both normal vectors. It's orthogonal to both normal vectors, right? Now, if it's orthogonal to both normal vectors, how can we find V? Well, we've seen this already, haven't we? To find V, all we're going to have to do is do what? How do we find a vector that's orthogonal to two vectors? All I have to do is cross them, right? So V, in other words, is just the cross product of n1 and n2. Writing this out explicitly, we've got I, j, k, 1, 1, 1, and 1, 2, negative 3, right? Or sorry, 1, negative 2, 3 is what it was. So you cross these things, just continuing that along. What does that give us? That's going to give us I times, actually, I'm not going to write it that way. I'm going to write it as 3 plus 2, I, minus, the j term is going to be 3 minus 1, j, plus negative 2 minus 1, k, or in other words, 5i minus 2j minus 3k. And if you take the dot product, you see this. 5 minus 2 minus 3, that's going to be 0. 5 plus 4, 5 plus 4. Now we can wonder reasonably if we actually calculated this correctly. So it's certainly orthogonal to the first of them, but 5 plus 4 is 9. Okay, so it does work out. 5 plus 4 is 9, minus 9, so we're good. So this does, in fact, work out. So that tells us, in other words, that this is our direction vector. That's our V. We're using the point 1, 0, 0. So maybe that's our point over here. So what are our symmetric equations? Remembering that they're going to be x minus x naught. In this case, that's just x over a, that's 5, equals negative, so x minus 1 over 5, rather, over, so is equal to negative y over 2, which is equal to negative z over 3. There are symmetric equations for our line of intersection. Okay, very good. Now, there's one other thing that we want to look at here, and that's distance from a point to a plane. So I'm actually going to stop recording and then restart recording so I can break this up for people watching elsewhere.